Hey everybody, today we get to talk about something really exciting, the Big Bang, one of the most interesting and controversial topics we'll talk about. Before that, let's remind ourselves of the evidence that the universe is expanding with this quick quiz. There you go, answer that on Moodle. Okay, let's get into it today. We left off talking about the Hubble-Lamaitre law that tells us that galaxies that are farther away are moving faster. Now we're going to relate this to this whole idea of the Big Bang. This comes from section 29.1. Alright, the Big Bang. And remember, this is a theory, so we're going to talk about the observations that sort of explain or help us to think that this is a good theory. And we're going to start with the observations we've already talked about, including the Hubble-Lamaitre law. So the Hubble-Lamaitre law, it was shorter to write when it was just the Hubble law, but I want to give Lamaitre his due. The Hubble-Lamaitre law says that the universe is expanding. Okay, that's where we left off last time. Says the universe is expanding. We can only explain what Hubble saw, these galaxies that are farther away moving faster, if the universe is expanding. So, if that is true, I'll go ahead and write that. So, how do we get to the Big Bang, or this idea of a beginning of the universe? Well, if the universe is expanding, that says that galaxies should be farther apart in the future. Okay? If something is expanding, things are getting farther apart. So galaxies will be farther apart in the future. All right, with me so far? Sorry, I'm trying to get rid of this A down here. My computer somehow wants to write in places that I don't like it to write. So galaxies will be farther apart in the future. So logically, that means that galaxies were closer together in the past. Hopefully that makes sense. Okay, if they're farther apart in the future, they were closer together in the past. Awesome. So what does that tell us? We roll the film backwards, so to speak, and if things were closer together in the past, it tells us that everything was close together before. Okay, that matter was once all packed together, all very, very close. And notice I've switched from saying galaxies to matter, because we talked about how galaxies formed, and we talked about dark matter clumps and protogalaxies, so we're rolling back to that time. There was a time when matter was all packed together. That is fundamental to the Big Bang. So it turns out you can use this Hubble-Lamaitre law to estimate how long ago that was, and we call that time the Hubble time. So, how long ago was it when everything was together? In other words, the amount of time it's been since all the matter was close together. So, the Hubble time is the time when the separation of matter was zero. There was no separation. Okay? This comes from our expansion theory, right? So the time when everything was together is the time of the Big Bang, or an estimate of how old the universe is. So we can use it to estimate the age of the universe. Okay. And currently, there's a little bit of debate about what that age is. Your picture here says 13.7. Depends where you look. I believe your textbook says 13.8 billion years old. There's some flex in this number because when we are measuring, this is that same graph. We show, this is distance versus time. Okay, this is a slightly different graph, sorry. Distance versus time. That the Hubble time depends on how slopey that slope is. And that depends on observations of redshifts of galaxies and distances to galaxies, which isn't perfect. So there are conflicting ideas about exactly how old the universe is. Anywhere from 12.5 to about 13.5, 14 billion years old. And that's because our observations are not perfect. It's very hard to measure distances in the universe. But we're going to go with 13.8 as our best guess right now. So just relating this back, I said this, but just to write it, the Hubble time, okay, that moment, the Hubble time moment is when the Big Bang occurred, okay, is called the Big Bang. And we will learn that this is actually not a very good name for this event that occurred, because it's not an explosion. It's not galaxies flying away from each other. I have a video for you that says that a better name instead is the everywhere stretch. Think about that rubber band and those paper clips. Space-time began to expand. There wasn't a bunch of galaxies that exploded. Look at the picture over here. We didn't have a huge explosion and the galaxies blew out into already existing space. No, there was no already existing space. Space itself had to expand, and the expansion, stretching the rubber band, carries the galaxies, carries the matter with it. So everywhere stretch is a much better name, and we'll get into that a little bit. You're going to have a lecture tutorial and some videos and all kinds of cool stuff to really think about this more. Okay, let's just, before you get to that, you are going to be doing an assignment where you watch a video. I'm going to have that assignment on Moodle and have that video link to explore these ideas. Okay, so that's coming up. But before you watch all those videos, do the lecture tutorial, clickers, all that stuff, let's talk about what the Big Bang means. So according to the Big Bang Theory, what happens? What is true? So according to the Big Bang Theory, what is the consequence of having this moment where all the stuff was together? Well, the first consequence is that the universe has no center. This may seem really odd because you think, well, didn't that Big Bang happen somewhere? But no, it happened everywhere, the everywhere stretch, because everywhere was all together in a single spot. Again, think of those paper clips, right? If we look at a different paper clip, it still looks like the universe is moving away, right? No matter where we are, the universe looks like it's expanding. So everywhere is the center, or there is no center. at all. The other thing about the Big Bang Theory that's important to keep in mind here, or the next thing, is that this expansion doesn't affect matter. Okay, so the expansion does not affect atoms, stars, or other laws of physics. What do I mean by that? I mean that your atoms are not getting bigger as the universe expands. The galaxies do not get bigger as the universe expands because gravity is holding that stuff together and the atomic forces are holding those atoms together. The paper clips don't get bigger as the rubber band stretches. Okay? All right. What's another consequence of the Big Bang Theory? Well, it happened everywhere. I sort of said this already when I said the universe had no center, right? It looks like it's expanding everywhere. So that means that the Big Bang happened right here. It happened everywhere. This is odd to think about, but there was no other where. There's no center, there's no edges. We kind of have to think about it in terms of infinity, which is a very hard concept, as you would see in the video that has the writing assignment. Okay. So, what else? Everything, and everywhere in the universe was once all together in a tiny, tiny space. Okay? Everything in the universe, all the matter that exists, was once in a tiny volume. Tiny, tiny, tiny. Okay, everywhere, every when, all of space and time and matter, everything, right? And it expanded incredibly rapidly. It started out so small we can't even imagine it. But within a 50th of a second, it was the size of Earth. In a day, the size of the solar system. So it got bigger really, really fast, and we'll explore that more. But just imagine everything, everywhere, in a tiny, tiny space. Matter was created actually after the moment of the Big Bang from energy. So this goes back to Einstein. E equals mc squared. Energy and mass are equivalent. They're the same thing. So back in the very, very first fractions of seconds of the universe, there was no matter, no atoms as we think about it. But matter was created from energy after that initial moment, after the Big Bang moment. Okay. About 100 seconds or so after, there started to become the first things that we would call matter, the first types of little protons and other particles. So it was a ball of energy, hot, tiny, dense, and then as it expanded, it allowed matter to be created. Okay, so you're going to have some cool videos to watch, a writing assignment, I'm going to do another demo video, so follow the playlist and look on Moodle for assignments.